Hello and good time of day to you. My challenge this time is to try to get this Philips PM3214 oscilloscope working. I acquired it quite some time ago and was told it's faulty, but I don't know anything about the nature of the fault. I've already removed its outer case and carried out a brief inspection, looking for any obvious signs of damage, and there didn't seem to be anything clearly wrong there. I've also removed this rear panel from the case, and mounted on that inside this box here is the mains transformer, and it has a single secondary which connects to the power supply board on the back of the oscilloscope via this connector here. I have removed this transformer and I determined that its internal thermal fuse has failed. I don't know whether it's in good order apart from that. However, I'm not going to worry about that too much, because according to the manual, this unit can also be powered using a DC power supply of between 22 and 27 volts and capable of supplying at least 1 amp. So I'm going to connect up a bench power supply and see what happens. I've connected a power supply set to 24 volts and with a limit of just over 1 amp. That's already on, so let's try turning on the oscilloscope's main power switch, which is shared with the illumination control down here. It's on. The power light hasn't come on, but I can hear a rather unpleasant sound coming from the power supply board at the rear, so I'm going to switch it off again. That noise was certainly rather like a switching power supply that's struggling to start, or perhaps is being overloaded, so I don't want to leave it like that for too long. I thought it could be interesting to have a brief look at some of its features and its construction. For the most part, it's a fairly traditional dual-channel analog oscilloscope with a 25 MHz bandwidth. One slightly unusual feature is that it has a secondary time base, and that's configured by these set of controls here. I've only briefly scanned through the user manual, so I don't fully understand all of its features and what it can do. However, it seems it can operate as a delayed time base in the usual way to allow a more zoomed in view of a portion of a waveform that's on display. It can also be used as a secondary trigger and time base. So for example, one could set it up so that trace A is displayed according to this trigger level setting and this time base, but channel B is displayed according to this separate trigger level and this separate time base, and so that would make it easy to display signals of very different frequencies, or two signals that are not related to one another in frequency. Here's the rear of the instrument. There isn't a great deal to see here other than the power supply board on the left. As alluded to earlier, this takes a single AC input from the mains transformer or a DC input from an external power supply, and it generates all of the supply voltages needed. Most of these are fed to the upper PCB, which I'll show you in a moment, via these wires over here. It also generates a high voltage AC output, and that's fed to this grey cable down here. That's rectified to produce a minus 1.5 kilovolt supply that's connected to the CRT's cathode. It's also fed to a network of diodes and capacitors housed in a black plastic box down here, and that generates a positive 8.5 kilovolt DC supply that's connected to the second anode on the side of the CRT. Another slightly unusual and useful feature of this oscilloscope is that its chassis is not connected to mains safety earth. It's double insulated due to the mains transformer being housed in an isolated plastic box on the rear panel. This can be very useful, as it means it can be connected to a device under test without having to tie some part of that device's internal circuitry to the mains earth. It does of course also mean that one has to think carefully about what one's connecting it to, otherwise the whole chassis could become connected to a high voltage with respect to earth, and of course that could be very dangerous. I don't think modern safety standards permit this scheme to be used in newly manufactured equipment. The chassis would have to be tied to the mains earth, or it would have to be fully isolated with isolated and inaccessible inputs. Nevertheless, I think this setup is perfectly safe so long as it's used with a bit of thought and care. Here's the upper PCB, and it's home to almost all of this oscilloscope circuitry. I rather like the design. It's certainly not something one would find in a modern piece of equipment. Even some of the transistors, for example these ones over here, are mounted in sockets, so perhaps that'll be handy should any of them need to be replaced, though I'm not sure which criteria were used to decide which transistors deserved sockets and which didn't. It's almost entirely a discrete transistor design. There are a few 7.4 series logic ICs over here, and a handful of other integrated packages. I'm not sure what all of them are, though I looked up the part number on one of them and found it was a transistor array. There's no silkscreen on this circuit board to indicate which components are which and what any of the controls do. However, I have got this clear and very helpful diagram that shows the location of every single component. Here's the view from underneath. I point out a few things that stand out to me. Over here we can see the circuitry for the input of the two channels A and B. Down here is the on-off switch and the potentiometer that controls the brightness of the graticule illumination. The bulbs responsible for that, I think, are driven via this power transistor mounted down here. Over here there's a length of spiral wound wire connected between these points and these points. It goes up here and there's a length contained inside this plastic container. That's clearly a delay line, and I'd imagine it's used to compensate for the delay in the trigger circuit to make sure that the trigger point of any waveform can appear on the left hand side of the display. Many of the front panel controls are hidden in here, so I think I'll have to do a great deal of dismantling if any of those need to be accessed. However, most of the interboard connections are on multi-way connectors like these, or single pin connectors like these that can be just pulled off and pushed back on again. So long as I go carefully and take some photographs and label things, I don't think it'll prove too difficult. In fact, I'll probably fully dismantle it to carry out a close inspection and do some cleaning, even if that turns out not to be necessary for the purposes of repair. I'm going to turn the power on again, and as quickly as possible I'm going to measure the voltages output by the power supply at this connector here. It's switched on and I can hear the unpleasant whining sound again. I want to try to determine whether the power supply is at fault or whether it's being overloaded, so I've unplugged this connector from the top PCB. Now there are a few other connections from the power supply to other parts of the oscilloscope, but most of it is powered via this connector. So I'm going to try turning the oscilloscope on again and measure the voltages at this plug. I'll be very careful how I hold it, as if the supply is working, there should be plus and minus 180 volts present here. So I have a voltmeter ready. We'll turn the switch on. And this connector here should be minus 180 volts. Minus 189, that's close enough. Plus 180 should be here. Yes. Then plus 38. Near enough, I think. 12 volts. This should be 5 volts. And finally minus 12 volts. So certainly that's a big improvement over before, where the voltages are all far too low. They're now fairly close to what they should be. And if we have a look here on the display, there's a very bright dot in the center of the CRT. That's probably not good for the phosphor coating, so I'll switch it off now. But that's a good sign too. It suggests there's no problem with the CRT. Well, there could be a problem, but it's emitting electrons, etc. So that's a very good start. Here's a diagram of the power supply circuit. On the left is the mains transformer. That feeds this bridge rectifier here. And this connector marked X7 is for the external DC input. This diode here provides reverse polarity protection for the rest of the circuit in case the external power supply is connected incorrectly, and if that's the case then it causes this fuse up here to blow. These two lamps offer graticule illumination and their brightness can be adjusted by this potentiometer up here, which is on the front panel. I haven't analysed this part of the circuit in detail, but clearly it's an oscillator that drives the primary side of the output transformer. Most of the generated voltages come from a single winding of that transformer that has many taps. There are separate windings for the CRT high voltage supplies, and a separate winding shown down here for the CRT heater filament. It took me a minute or two to notice after first looking at this diagram that the voltage up here is negative with respect to the voltage down here. That's an utterly bizarre way to draw a circuit diagram. It's been off for a while, so hopefully that will have allowed all capacitors to discharge, especially the ones across any of the power supply rails. I'm going to use a multimeter to measure the DC resistance between the 0 volt rail and the other power supply rails at this connector here. Multimeter is connected to these leads with plugs on, so that one can stay there. Hopefully this will reveal which, if any, of these are being overloaded. And you can see on the diagram which is which. This one up here is the minus 180 volt supply rail. I'd expect the values to start off relatively low and then climb. That's very high, so not a problem. The next one is the plus 180 volt supply. Very high again. Next one is the 38 volt supply. Probably just a strange coincidence, that's about 38 kilo ohms. Moving on to plus 12 volts. 186 ohms, low-ish, but quite possibly correct. 5 volts. The auto ranging of the meter struggling a bit there, but it's all over the place. I'd expect this to probably have the lowest resistance because there are probably quite a lot of different devices connected to the 5 volt supply. It's jumping all over the place, but none of the readings are particularly low, so I'm not worried about that. Try the next one, minus 12 volts. Again, it's struggling with the auto ranging. Can it make up its mind? A bit of wiggling of the connector, and that's not very good. Under 2 ohms, that's definitely a problem there. The multimeter is still measuring the resistance between the 0 volt and minus 12 volt power supply connections to the top PCB. I want to try to find out whether this near short circuit is due to something on this PCB or one of the number of components that are connected to it. For example, there are a number of flying leads with plugs a couple plugged in at the front here, and quite a few more underneath. So let's try disconnecting these one at a time and see whether that has any effect. Before I turn it over and try removing the connectors underneath, let's also see whether any of the front panel controls have any effect. It hasn't had much effect so far. Seems to make a slight difference. These are the coupling controls for the channels. Ah, that made a difference. That's the main time-based control. The exposition control also seems to have some effect. Ah. If I move it, turn it quite hard to one side, the reading jumps up to nearly 300 ohms, which is perhaps a more reasonable reading for it to normally have. I think I might try leaving it in that position and powering it on briefly to see whether that's made any difference. I've adjusted a number of the controls back to perhaps slightly more sensible default positions, but verified the DC resistance between the 0 volt and minus 12 volt power supply lines is still about 300 ohms, and I've connected a bench power supply back to the DC input at the rear. The power light on the front has come on straight away this time. That's a good sign, surely. Let's see whether a trace will appear. Looks a bit more promising. The A channel is enabled. I can move it up and down. Seems to be a working time base. I'm going to very carefully measure the voltages at the power supply connector on the top PCB. Let's see whether they now have reasonable values. I would think they probably have. So the first one should be minus 180 volts. That's the one furthest from the front. I should think that's fine. The next one should be plus 180. And then 38. Plus 12. Five. And the last one minus 12. Excellent. I don't think there's anything at all wrong with the power supply in this device. So what I think I'll do now is get out a signal generator and see whether it will display the waveform from that. Here it is displaying a 100 kHz sine wave at 5 volts peak to peak. The vertical scale is set to 1 volt per division and the time base to 5 microseconds per division. Here's the same signal displayed on another oscilloscope set to the same configuration. Try a square wave, a triangle wave, change the vertical scale. That's down to 5 volts per division. Put it back to 1 volt per division. So the basics of channel A at least seem to be working. The triggering is set to auto. Let me try switching it to normal DC triggering. Still triggered. If I adjust this control here, the trigger level, that has the expected effect, although the range of adjustment over which it triggers seems rather small. Set it back to auto. Let's try channel B. And switch triggering to channel B. There seems to be a problem with triggering from channel B. I'll switch it back to channel A and switch the triggering back to channel A. That's still working. I'll try enabling the delayed time base. Let's see how that works. I think I switch. I see, and this is the delay time. Okay, so it highlights a portion of the waveform. Can I display that portion separately? Yes, and its time base is controlled by this separate control here. If I switch these both in, aha, that's rather what I was expecting. So now we can see a magnified view, or a shrunken view even, I think, if we set the time base appropriately. Probably not so useful. Quite like that. It's certainly easier to use than the Tektronix oscilloscope I've got. I always seem to manage to get that into a slightly confusing state when I use its delayed time base. So I don't think there's too much wrong with this oscilloscope. Certainly some of the controls are rather dirty and probably need cleaning. Triggering from channel B doesn't seem to work properly. And of course there's that problem with the exposition control, which I've been very careful with, as that sometimes shorts out the minus 12 volt power supply, which I would think is probably a slightly more serious problem than it simply requiring some cleaning. However, I think my next step will be to more or less completely dismantle this instrument, mainly so I can get to the front panel controls and test them and clean all their contacts, etc. Following the instructions in the manual, it wasn't too difficult to remove this section of the front panel, though it's worth reading the instructions carefully and taking a slow, methodical approach. There are a few very short leads at the rear of this module that plug onto the main PCB, so disconnecting them was quite a fiddle, and I imagine it won't be easy putting them back. Quite reasonably, the instructions say that one of the very first steps should be to remove all of the plastic knobs from the controls, and that wasn't too difficult. Just following the instructions did the trick, other than for these controls that can be rotated and pushed and pulled in and out to operate switches. The instructions say that the end cap of the knob should be removed and then the metal insert unscrewed. I found it almost impossible to remove the end cap. It was easier to pull the knob off this metal inner, and now these metal mounts can be removed separately if necessary. Here's a section of circuit diagram showing the X amplifier. I've labelled what I believe is the control that adjusts the X position of the trace, and it's this dual gang potentiometer shown here. That's the component that seemed to sometimes cause a short of the minus 12 volt supply, and that looks feasible because one of the gangs, this one here, is directly connected to the plus 12 and minus 12 volt supplies. Furthermore, inspecting this control I think has revealed the cause of the problem. This is the X position control, and if you look closely down in here, where this yellow wire connects to one of its tags, you might be able to see that it's pressed against the bracket of the time-based control underneath it. And with the multimeter wired up, I've confirmed that just some gentle jiggling of this control sometimes causes a connection between the two. I'm rather surprised that no one at Philips noticed this potential problem. Hopefully it won't be too difficult to remake this connection, perhaps by bending the tag back slightly so the problem will go away. Also, during disassembly, for some reason or another, the switch part of the control next to this one here, the trigger level control for the delayed time base, has failed. I'm not sure what has caused that, so I'm now going to dismantle that to see whether I can repair it, and if not, I'm going to have to look for another control. Here's what I found inside the switch part of the trigger control for the delayed time base. I can't work out quite how it's supposed to go together. However, I think this piece of spring wire was originally one piece, like that, and I rather doubt it'll be possible to repair that. It turns out nothing was broken, though I can't work out how the parts managed to displace themselves. I spent a very long time experimenting with them to try to understand how they could fit back together again, but wasn't able to come to a conclusion, so I took apart one of the other switches, and this is what I found. Be thankful I've not asked you to watch me reassembling them. It took several hours, and at least half of that time was spent crawling about on the floor looking for those evil springs. If they were just breathed on or looked at in the wrong way, then they hurled themselves off into the air. I've more or less completely dismantled this control assembly, cleaned everything, applied some lubricating contact cleaner to all the switches and potentiometers, rearranged the wiring in several places to hopefully avoid any short circuits, replaced the BNC connectors as the originals were rather corroded, and put it all back together again.